this. Okay. Superposition theorem. Superposition theorem is for a circuit like this. If I have a voltage source here, I have a resistor here, I have a point A, I have a point B, and I have another resistor here, and I have another voltage source over here. So we'll keep it simple. So I have a VS1, I have a VS2. I will have an R1, I will have an R2, and I will have an R3. VS1 will be 10 volts. VS2 will be 8 volts. R1 will be 20 ohms. R2 will be 20 ohms. And R3 will be 30 ohms. And the first thing you do for any circuit, it's got DC voltage sources, you're going to put polarities on here. This is negative, this is positive, this is positive, this is negative. So as you look at these voltage sources, there's no way that you can immediately say what your voltage total will be. And that's really not the important issue at this point. When you're doing superposition theorem, you're analyzing for a voltage, for a circuit that has multiple voltage sources, but what you're analyzing for will be the currents and the voltages of the resistors. Okay? So superposition theorem will be used for multiple VS for voltage source circuits, not easily reconciled for series aiding, nor for series opposing. If you look at this voltage source and this voltage source, they're not in series. They're not in the same current path. They're separated by node B, they're separated by node A, and there's resistors between them. So unlike we had in the previous example of series aiding and series opposing voltage sources, and we had an easy way of reconciling them based on polarities and directions of electron current flow and building a T-chart of current to the left, current to the right. We can easily reconcile a voltage total for series aiding or series opposing. We can't quite do that here. I don't have voltage sources in series. I don't have them, and because they're not in series, we cannot use the previous method. So how do I analyze this based on having separate voltage sources? I need to find voltage.
If you look at them both, though, if you look at them both, the negatives are, if you draw like arrows around, they go, the current goes the same way, right?
It turns out that they are helping each other, but we don't have a total that you can reconcile at this point. It looks like they're helping each other out, okay? But we don't have anything that will allow us to mathematically do any calculations yet. So the method of solution, so here you go. Your solution method for superposition theorem will be the following. Step 1, replace VS1 with a wire and solve for all voltages and currents. Then 2, replace VS2 with a wire bringing back VS1 and solve for all voltages and currents. And then 3, algebraically add all voltages across resistors based on current paths. Number 4, check results using KVL. So those are your 4 steps as your solution method for superposition theorem. They're stated as replacing the voltage source VS1 with a wire and then solving all voltages and currents. Then you're going to replace VS2 with a wire, bringing back VS1 and solve for all voltages and currents. Then in step 3, you're algebraically going to add all voltages across the resistors based on their current paths. Now, there's a very special operative word here. You're going to algebraically add all voltages based on their current paths. And then finally, you're going to check results using KVL. So this is a multi-step process. So we will go ahead and begin by doing this. Taking the circuit, I'm going to do a redraw. And in this redraw, I'm going to replace voltage source number 1 with a wire. So my point A is here. I will have a resistor here. This is R2, 20 ohms. This is my R3, 30 ohms. And I will have a voltage source over here. This is VS2, 8 volts. And this guy comes down. Here's my node B. And this guy comes over to here. And I'm replacing this with a wire. R1 is 20 ohms. So this is my step 1. Step number 1. Have I replaced voltage source 1 with a wire? And everything else remains the same. R1 is still 20 ohms. Point A is still A. I have 30 ohms over here for R3. Here I have 20 ohms for point B, and I have 8 volt source. Everything else is the same. The polarity on that voltage source has not changed. It's still going to be negative on top and positive on the bottom. So now I have to do an analysis on what's happening with this particular schematic. So if I go to and analyze what's happening on this particular schematic, I need to calculate voltages and currents. So let's go ahead and do that. What do I need to do with this particular circuit? What do I have here that I can simplify, because I have 3 resistors and I got to get it down to an RT before I can calculate total current. So question goes to Gabriel. What do you think? How did we simplify circuits previously? This has only got 3 resistors and 1 voltage source. We've done this a few times. What do you remember?
Adding it?
What's that?
Adding it, if I'm not mistaken.
What are we adding? What's the relationship between these components that you're adding? How do we analyze the solution for simplifying this? What did we do in the past? Question goes to, let's see, Andrew, what do you think? Or Kyle, I haven't asked Kyle yet. What do you think we should do, Kyle?
Since you have two 20 ohm resistors, can't you use the one method in order to? Wait, can't you add them because they're in series, the 20 and the 30, I think?
Is the 20 and 30 together? Okay, all right, well, that's an interesting thought. So here, if you go back to what we had done before, we had a circuit, and in order to analyze the circuit, we had a process. That process was called what? Circuit reduction. How do we reduce the circuit? We had to do what? We had to redraw the circuit. Why did we do that? We did that in order to simplify. And in the simplification process, we were able to generate equivalent resistances. Ultimately, we want to take a network of resistors, these 4 down to 2, down to 1. How did we do this? We did this by, if this was my voltage source here, didn't we put our eyeball on a part of the circuit completely opposite of the source, say on this side? And if you're looking back at the circuit from the side, you look at this wire, and what do you see? You see these two have a special relationship. What did we do? We combined them into an REQ1. We found that these two resistors over here could also be combined, and then these two were in parallel to this. So the method doesn't change for our analysis. The process doesn't change for our analysis. So if we're using the same process, using this method for this purpose of simplification, how do I play with this particular circuit? Where do I need to put my eyeball? The eyeball has to be as far away from my voltage source as possible. Here's my voltage source. Here is my eyeball. Looking at the circuit from this direction. And it sees a wire. On that wire is a jumper wire. What else is on that wire?
R1 resistor.
R1. Okay, is there anything else on that wire before it connects to node A and B?
No.
No. So what is the relationship between R1 and R2? Is there a relationship? Are they in series? Are they in parallel? Do they have a relationship? Are they independent of each other?
They're series.
Series means they're in the same current path. Are they in the same current path? Does the current that flows through R1, is that the same current as what flows through R2?
It's in a single.
No, they're not the same current path. Because if you remember, if we go to draw the arrows, here's the electricity flowing from the voltage source. Here's the electricity flowing through this resistor. Here's the electricity hitting node A. What happens at node A? The current split. So they are not in the same current path because the current split. And if there is a current split, they're not in series, because series means that they are in the same current path.
R1 and R2 are in parallel.
And what is the definitive reason that they are in parallel? Not because they're just because they're not in series does not mean they're in parallel. How do you prove from previous definitions that they are in parallel? What did we use for a definition for parallel in the past?
They share the same nodes.
Okay, So let's go ahead and follow that definition. Rolando, this right lead of R1
Yeah.
and the upper lead of R2, do they connect at a common node called A?
No, correct.
Now look at the opposite leads. Does the opposite lead, meaning the left lead here, does it connect with the opposite lead of R2 at node B?
Yes.
Yes. So based on the definition that we had before, I'm not going to take them and write it down here, but based on the definition of parallel, R1 and R2 are not drawn to look like they're in parallel, okay? They're not like this and they're not like this, but they are electrically in parallel with each other. And this is what you need to be able to look at and understand based on the definitions I've given you before. Okay, it's not a guess. What series? No, it's parallel. A series is parallel. No, you have to understand why it is in series or why it's not in series, why it's in parallel or why it's not in parallel. And there is another situation where they're neither series nor parallel. Okay? There's another situation I haven't shown you yet where they're not in series and they're not in parallel. So there's another condition. All right, but we won't talk about that now. So are we in agreement that R1 and R2 are in series, in parallel with each other? Yes?
Yes.
So that means
Yes.
I can point A here and here, and here's my source, like so. And this is my VS2, and this is 8 volts, and this is my R3 of 30 ohms, and this is my, make this REQ number 1. And REQ1 says R1 in parallel with R2. So I got a pair of 20 ohm resistors in parallel with each other. What is my total? Am I going to use reciprocal method? Am I going to use product over sum? What am I going to use? What's the fastest way to do this?
Reciprocal.
Sure, reciprocal will always work, okay? So you can take just 20 reciprocal and you add it to 20 reciprocal equals, and what do you get? When big dot, what do you calculate? 20 parallel with 20.
Yeah.
Kyle, what do you have?
10 ohms.
Okay, end up 10 ohms. Because there was another way we could do this. Another way we could do this is, are they identical values?
Oh, yeah.
Yes.
Yeah. And how many do I have that are identical? 2.
2.
So what is 20 divided by 2?
10.
Okay, isn't that faster than reciprocal?
Yes.
In this particular case, it is. Yes? So far, so good. Now, that being said, do I have enough information to take this down to an R total?
Yes.
So what is my value of my R total? Andrew?
I'm working on it right now.
Well, what is my relationship in this drawing that I have? Take a look at my drawing.
They're in series.
I have an R3 with what relationship with REQ1? Series.
They're series.
What is the value of R3?
30.
What is the value of my REQ1?
10.
So if I have these two in series, what's my R total?
40.
40 what?
Ohms.
40 ohms.
40 ohms. There you go. Okay. So that you can do with mama's calculator between your ears. Yay. All right. So we need total current. Do I have enough information to determine total current? So my IT, according to Ohm's law, is going to be equal to V total over R total. Yes?
Yes.
Is that going to be 8 volts over 40 ohms? So what's this work out to be?
0.2.
8 divided by 40. Pauline, you got a number?
I got 25 milliamps.
I got
25 milliamps.
200 milliamps.
Somebody's got 20
Fine.
milliamps.
200 milliamps.
I got 200.
Somebody's
200.
got 200 something.
200 milliamps, sorry.
200 milliamps.
Okay.
So
Because mine also shows
200.
200 exponent negative 3. So 8 divided by 40, 200 exponent negative 3. So this is going to be 200 milliamps. Are we correct there? It's just 8 divided by 40, which is what I have here. 8 divided by 40, there's your 200 milli. Well, is this the same method from here on down? Is this the same method as we employed previously for analyzing our circuits? Here's the voltage source. You put your eyeball farthest away from it. You look at the relationship between the resistors. You discover R1 and R2 are in parallel. You calculate those, reciprocal, shortcut, product over sum, whatever, doesn't matter. You're going to end up with 10 ohms. The 10 ohm REQ1 has a very unique relationship with the original R3. They're in the same current path. They're in series. You combine these two to a single total, 40 ohms. And then 8 volts into 40 ohms gives us 200 milliamps. So now what you're going to do, when we have this, the method is to shoot back upstairs, okay? So as we shoot back upstairs, this is the information we have. Question?
If everything's pretty much the same, all you got to do is put it in 10 volts now, right? 10 divided by, 40 divided by 10 volts.
There is no 10 volts here.
No, because if we got to rebuild and do the other side, everything should equal out to the same, right?
No, we're going to take this
We'd
step by
be
step.
analyzing on the other side as well.
Leave the 10 volt thing out for a separate piece of paper. That's going to be on a separate piece of paper.
Okay.
Okay. So we're going to analyze just this portion of it, step 1, because we're not into step 2 yet. We're far from step 3. So we're only in step 1. We've replaced VS1 with a wire and solved for all voltages and currents. We are in the process of doing this. Okay. So now we're into the simple series circuit. Current comes up through here, goes over to here, comes down, over to here, and back up to the source. So does electron current in fact leave the negative side of the voltage source, goes through the circuit, and comes back around to the positive side of the circuit, the positive side of the voltage source?
Yes.
Is that in fact what we stated earlier here? Current leaves the negative side of VS and returns to the positive side of VS. And is that what we have here? Leaves the negative side of the voltage source, goes through the circuit, and then comes around back here. So far, so good. We are done with this drawing. Now we have to take this upstairs to this step. If we take the information up here, what can we take? Well, polarities. What else can we take? Direction of current flowing out of the source. That's 200 milliamps right there. And it flows through R3. Ah, interesting. And then it flows down through R1 and back this way and back to the source. Do these arrows match the direction of arrows from my very basic RT circuit? The directions are the same. Guess what? Do I happen to have a final direction of current through R3? I do. So it means I can start setting up a very special table. And this very special table will be set up for R1, R2, R3. It will be set up for a V column. It will be set up for an I column. And it will be set up for a direction column. Okay. So there's 3 columns, VI and direction. So for R3, do I have a direction of current flowing through R3 I can fill into this chart? Is the direction through R3 flowing to the left, as evidenced by this drawing? The answer is
Yes.
and it's flowing to the left. So I draw an arrow to the left. Do I have a value of current flowing through that resistor? The value of current happens to be 200 milliamps. Can I calculate for a moment what the voltage is on that particular resistor? Don't I have, remember, for Ohm's law, put it on here just for reminder, V, I, and R. So if I want to calculate V and I cover up the V, isn't V equal to I times R? Do I have an I of 200 milliamps? Do I have an R of 30 ohms? Can I multiply the two together to give me a voltage?
Yes.
Do that. 0.2 times 30. How many volts?
6.0.
6 volts. Okay, we're done with R3. So far, so good. Hey, hey, pat yourself on the back. Now, we're done with this circuit. So we simplified down to here, and now we're bringing the information up, and now we're done with this as much as we can, because we found one of the original currents through one of the original resistors, the R3. Now you take this information back upstairs to here and analyze what's going on using your currents. So out of this source, you have 200 milliamps. 200 milliamps. And it's flowing in here, and the 200 milliamps will split. How will they split? Well, part of the current goes here, part of the current goes here. Well, guess what? These happen to be equal in this case. So if they happen to be equal, how do these two resistors at 20 ohms split this equally? How much current must go through each one of these? Andrew. I got 200 milliamps flowing here, and then it's split equally between R1 and R2.
100 milliamps each one?
Yeah, it's basically splitting it in half. So here's my current, 100 milliamps in here and 100 milliamps in here. Boom, done. Can I write down the direction of currents? What is my direction of current through R1? My direction of current through R1 is which way?
Left.
Left.
What is my direction of current through R2? Down.
Down.
Down. Okay, so far so good. And can I, for a moment, calculate with 100 milliamps what my voltage will be for R1 and R2? 0.1 times 2. So. One times 20. Pauline?
I'd use the voltage divider.
Use Ohm's law. Use Ohm's law. If you had decided we have 100 milliamps through here, 100 milliamps through here, you simply take 100 milliamps times 20, and that will give you
2
what? Apples?
volts. 2 volts.
Thank you, Andrew. So 2 volts and 2 volts. Are we good with that part of our analysis so far?
Yeah.
Yeah.
Hot diggity dog. All right, that's great. So all of this is based on step number 1. Okay. Okay. So what I'm going to do is leave the paper. We're now going to do step 2. So step 2 says, what are we going to do? We're going to place VS2 with a wire but we bring back VS1 and solve for all voltages and currents as we've done here. So with a separate piece of paper, I'm going to redraw the circuit based on step 2. So here is step 2. So step number 2. And step number 2 says I'm going to bring back, so here's my point A. I'm going to bring back my VS1, and VS1 was equal to 10 volts. Here's my point B. So here's my original R1 of 20 ohms. Here's my original R2 of 20 ohms. Here's my original R3 of 30 ohms. And what am I going to do with my VS2? My VS2, I'm going to replace.
You're going to put a wire in it.
With a wire. So here's a wire. So has my step 2 conformed with step 2 of my statement over here? Have I replaced VS2 with a wire? Have I brought back VS1? And now I'm about to solve for all voltages and currents. Is my schematic matching what we asked us to do based on these directives? The answer is yes. Okay. How do we analyze this? We did this 2 weeks ago. So this one should be a piece of cake. Where's my voltage source? On the left-hand side. Where do you put your eyeball? Way over here, and you're looking at this piece of wire. As you look at this piece of wire, what relationship do you see between which resistors? Rolando.
Yeah, R1 and R3 are in parallel.
Which resistors again?
R2 and R3
Okay, all right.
are in parallel.
Yeah, R2 and R3 are in parallel. Is everybody in agreement with that? Is R2 and R3 in parallel with each other electrically?
Yes.
Yes.
Yeah, is the upper lead of R2 and this lead of R3, are they connected at a common point called A? And look at the far lead of R3. Is the far lead of R3 connected to the far lead of R2 at a different common node called B? So yes, these two are in parallel with each other. So that means I can draw a redraw similar to what we've done before, but with these sources. So I will have here, 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 here. My VS1 is still 10 volts. I still have an R1. Here's point A. And come down here. Here's my point B. And I'm going to replace these with a single equivalent resistance, REQ, number 1. And in this number 1, and in this case, this is equal to R2 parallel with R3. So this is equal to 20 ohms in parallel with 30 ohms. How do I reconcile this? I could do product over sum. I could do reciprocal. Would you please calculate what that equivalent resistance works out to be, please?
12 ohms.
12 ohms. Okay, Rolando. How many people agree with Rolando that this will work out to be 12 ohms?
Agree.
Okay, 12 omega. Okay, everybody okay with that? Cool. All right. So we've taken 3 resistors and now brought it down to 2 resistors. Very good. What else do we need to do to continue with this to a successful conclusion? One more redraw. One more redraw. My VS, 10 volts. VS1 is 10 volts. Oops, Pauline. She's coming back. There she is. Okay. Yeah, welcome back. All right. So we've found that these two are in parallel with each other. It gave us 12 ohms. Simplified to REQ1. REQ1 and the 20 ohm resistor are in series with each other. So they come over to give us a total. Here's my total. Our total works out to be what value, guys and gals? These two are
32.
in series. So it
32.
should be 32 ohms, yes? Are we good with that? Do we have enough information to determine my current? So this is
Yes.
positive, negative. So the current will leave here, come up, flow up, and over and back to the source. So my I total is going to be equal to V total over R total. And that's going to be equal to 10 volts over 32 ohms. 10 divided by 32 equals, question goes to Pauline. Do you happen to have that number for us?
312.5 milliamps.
Excellent. So 312.5 milliamps. Is everybody in agreement with that current?
Yes.
Okay.
How do we get the 12 ohms again?
How do we get the 12? It was a good question. It was the 20 ohms parallel with the 30. So we used reciprocal method, and I'll demonstrate that for you. So if I hit clear in my calculator and clear the display, and I take 20 and hit reciprocal, and I add it to 30 and hit reciprocal, then hit equals, then I have to hit reciprocal and equals one more time, and the answer works out to be 12.
I see.
Okay, are we good with that method?
Yeah.
Okay, good question. If you at any point in time there's a number you don't quite get, I'll be happy to review it with any of you. Okay, we're good with the 312.5 milliamps in the circuit, yes? Do we have enough information to take this up to here?
Yes.
Yep, let's go ahead and do that. So this will be positive, negative. Current will flow here, up through the equivalent resistance, over through R1 and back to the source. Whoa, guess what? That 312.5 milliamps flows through one of our original circuit resistors, R1, does it not? Do I have a direction and do I have a value of current? I do. We'll hold that thought. Taking our current analysis further, let's go further up. If I take my current analysis further up, I have positive and negative. Current leaves here, flows here, hits this node. That's 312.5 milliamps here. It splits. Which way does the current flow through R2, my friends? Up, down, left, or right?
Up,
Up.
down.
Okay, we are in agreement. It flows here. How about the current through R3? Up, down, left, or right?
Left.
Goes here.
To the right.
Up through here, and then through R3 is what? To the left. Then these two currents combine at node A to go through R1, and that's 312.5 milliamps going back to the source. So you need to determine how this current splits. What method do we use to determine how this current splits? Couple methods. You could use Ohm's law. You could use
Current divider formula.
I would highly recommend current divider formula. So use CDF. CDF is current divider formula. And the general form of the formula is always given as IRX. is equal to RT over Rx times I total. Now, how do I apply that to this? Because what's in parallel with what? Well, we determined that these two resistors, R2 and R3, were in parallel to give us the equivalent REQ1 of 12 ohms. What numbers do I put in here for the following calculation? If I'm looking for IR2, now I have R2 is what I'm looking for. So R2 has to go in the denominator. And the I total in this case is I total. What do I use for RT? Do I use the 32 ohms for RT?
No, the 12. I mean the REQ total, yeah, 12 ohms.
Yeah, I have to use the 12 ohms. I cannot use the 32. The 32 is RT for the entire circuit. This RT in the current divider formula only applies to what is in parallel. And the only part of this circuit that's parallel is R2 and R3. So R2 and R3, they parallel total to become how many ohms?
12 ohm.
12 ohms. So what I need to have here is REQ1. So now let's go ahead and fill this in with some numbers. So this is going to be equal to 12 ohms over 20 ohms times my 312.5 milliamps. So my IR2 will calculate to be what value? Question to Kyle. Haven't heard from you in a while.
Working on it right now.
Good.
I got, this is right, 187.5 milliamps.
187.5 milliamps. Yeah, you spoke it correctly. I did not repeat it correctly. I apologize. But yes, it's the same number as what I got on my calculator. If we take 12, divide by 20, and we multiply by the current 0.3125, we end up with 187.5 milliamps for IR2. And in which direction does it flow through IR2? Does it flow up, down, left, or right?
Down to up. Or up.
Yes.
My bad.
Just up. From the bottom to the top means we are going in an upward direction, okay? Good. And then previously over here, from this drawing, were we able to deduce, actually before we jump there, let's go ahead and do one more calculation. And this other calculation will be for IR3. So IR3, how do I find the value for IR3? Would I use the same structure or formula? R3 goes in the denominator, multiplying by I total. And what am I going to use for R total in this case? REQ1. So if I go to put these numbers into the calculator now, my IR2 is going to be equal to, IR3 is going to be equal to 12 ohms over 30 ohms times 312.5 milliamps. So my IR3
125 milliamps. 125 milliamps.
125 milliamps. Who would second that?
Yeah.
I second
Excellent. My calculation also shows 125 milliamps. So we will go 125 milliamps. And what direction is this current? Up, down, left, or right through R3?
Left.
Left. How many people agree left? I hope the rest of you do.
Yes.
Okay, so we've gotten IR2, IR3, and then previously from here, I didn't write it down because I wanted to make sure we had space for all of the rest of this analysis. Let me get this here. Okay. We have one more current, which is IR1. And IR1 from our middle circuit, we determined was the full 312.5 milliamps flowing through it, yes? So this will be 312.5 milliamps. And which direction is it flowing through R1? Is it left, down, right, or
Left.
going through the left? Okay, this is valuable information that we have here. Very, very key information that we have here that we're going to transfer into our first sheet. So our first sheet, we happen to have this chart. And what I'm going to do is I'm going to mimic this chart right here. For R1, for R2, for R3. For the values of a V, an I, and direction. Okay. Now it's time to fill in this chart. So as I go to fill in this chart, take a look at IR1. IR1 is given as, in this calculation, 312.5 flowing to the left. Can I fill that information here? This will be 312.5 milliamps flowing to the left. Do I have information for IR2? IR2 is given as 187.5 milliamps. And which direction? It flows up. Do I have information for IR3? IR3 is 125 milliamps. And which way is it flowing?
Left.
To the left. So far, so good. And all this information is part of step number 2. We can fill in the voltages. Actually, the voltages don't matter because ultimately it's the currents that will decide what's going on with this. And we only have one set of voltages that really do matter. All right, so have we finished step 1 and have we finished step 2? What is left after we finish step 1 and step 2? What's it say in step number 3?
You gotta add them together.
Algebraically add all voltages across the resistors based on current paths. Well, actually, I think I want to change some words here. Okay. What we're going to do is I'm going to change this. We don't have to do the voltages because that's more work than is necessary. I'm going to make this simpler. Blank this out. And then here and here. I'm going to change it to these words. Add all currents. And instead of across, I'll make this through. We could do it the other way, but this is the method that we're using. So we're going to add all currents through the resistors based on the current paths. So there is one more VIR that we're going to do right here. I need some table space, so I'm going to use it. So for R1, R2, and R3, V, I, and direction. Okay, this is our moment of truth. So our moment of truth is this. Take a look at what's happening with R1. R1 has current of, in step 1, 100 milliamps flowing to the left. In step 2, R1 has 312.5 milliamps flowing in which direction?
To the left.
Left. Are both of
Yeah,
these
that's-
moving in the same direction? The answer
Yes.
is yes. So if they're both moving in the same direction, they are aiding each other. So my final direction must be to the left. And if they're aiding each other,
You'd
that
add
means
them.
I'm going to add the 100 milliamp to the 312. So guess what? That's easy math. 412.5 milliamps. Is that correct?
Yes.
Did I algebraically add the current through R1 from step 1 and step 2?
Yes.
Now let's see what happens on step for R2. R2, here I have 100 milliamps going down. Here I have 187.5 milliamps going up. Uh-oh. They're going in opposite directions, aren't they?
So
That
you
means
would take.
That means I have opposing currents. So what do you think?
So you would take the 187.5 and minus that by 100, which would give you what, 87.5 going up.
87.5 milliamps. You're right, Andrew. And the final direction is
Up
up. Why?
because it has the greater number.
Exactly. And here I have a phrase for you. The phrase is might is right. Okay? Might is right. And what do I mean by might is right is this. The stronger current will be the final direction of current. So if we look at R2, R2 has a current going down of 100 milliamps. R2 has a current going up of 187.5. The 187.5 is stronger. It is going up. That's got to be my final direction of current for R2. The difference between 100 milliamps and 187.5 milliamps is 187.5. Subtract this, leaving you with 87.5. Did we algebraically add these currents to resolve with this number? We added a positive to a negative. We ended up with this. Did we fulfill step number 3 for resistor number 2?
Yes.
The answer is yes. One more to go. Okay, take a look at R3. R3 has 200 milliamps going to the left. Over here, R3 has 125 milliamps going to the
Left.
left. They're both going in the same direction. What's my final direction going to be?
To the left.
To the left. What's my final amount of current going to be?
300
plus this would
25.
be
325 milliamps.
25 milliamps. Yes? Cool. Now, can I determine the final voltages based on these currents? Yes. The final voltages are simply Ohm's law. Okay? Simply Ohm's law. So in order to find my V, what do? I multiply the I times the R. Do I have a final current through R1? Do I have an ohms for R1? 20 ohms. So all I have to do, and here's the fast math. You can key in the millis and the micros if you want. I'll do it this way. This 412.5 milli is simply 0.4125. In decimal form is 0.4125. And I'm going to multiply that by 20. Bam. How many volts do I get there?
8.25.
8.25.
8.25. So that's fast math. Okay. So I have 8.25 volts. What's the fast way of multiplying this current for R2 times 20 ohms? The fast way to do this will be 0.0875. Or if you're more accustomed to, we'll do it this way, 87.5 second engineering -3. So there's my milli. And multiply this by my 20. And what do you all get?
1.74.
1.75 volts. Okay, if we use memory and everything, that's what we're going to have. And then the last one, 0.325 times 30 ohms. Because this will be multiplied by 30. So what will be my voltage here?
9.75 volts.
Come again with that?
9.75.
Excellent. 9.75 volts. How many people agree?
I agree.
So far, so good. Okay. Well, the magic is about to occur. Here's the magic. And this will wrap it up nicely. Because have we done step 1, step 2, and have we finished step 3? Did we algebraically add all the currents through the resistors based on current paths? We've got all that. We've calculated the final voltages. We actually didn't have to calculate voltages here and here because that's more work, but it will also prove that our work is correct, but that's not necessary. I wanted to save us some time. What's the very last step? What's it say? Check results using what? KVL. What was KVL? KVL was Kirchhoff's what? Voltage law. What's it say for Kirchhoff's voltage law? It says that the algebraic sum of all voltages in any closed loop, what? Must add to 0 volts. Is that correct? Oh, okay. And how many loops did we have in the previous example? We had loop 1, loop 2, loop 3, right? Well, let's see what happens in this particular analysis. So I'm going to do this with a new piece of paper. I'm going to do this a little larger. So here is A. And here is B. Okay, VS2 is 8 volts. VS1 is 10 volts. R2, R1, sorry, R1, R2, and R3. We already know the ohms. I don't have to write down the ohms. What I will write down, however, are the polarities. And so we have to, actually, we're going to do polarities of the voltage sources. So this is clearly negative, clearly positive, clearly positive, clearly negative. So far, so good? We couldn't tell from the original circuit what polarities would be across each of these. We have to rely on the information that we tallied here. And so relying on the information we tallied here, let's analyze what's going on here. What was the final direction of current through R1? The final direction was deemed moving to the
left.
Moving to the left and having a value of 8.25 volts. So R1 moving to the left and having 8.25 volts. Did I transfer that information correctly? Moving to the left of 8.25 volts, 8.25 volts. And the current was given as 412.5 milliamps. It's okay. We have it here. I don't need to put it up here just yet. How about for R2? For R2, what was my final direction of current? Up. And what was my value of voltage?
1.75.
So I'm going to draw this going up, and I'm going to write down 1.75 volts. So far, so good. And how about the last direction of current? The last direction of current of R3. R3 moves to the
left.
So I will go ahead and draw to the left. And what was the final voltage?
9.75.
9.75 volts. So far, so good. All right. So we're half a heartbeat away from proving all of this. Now, what did we say about electron current flow? We said electron current must flow from what side of a device through them to what side of the device. It always flows, but electron current must flow from the negative side through them to the positive side. So based on that definition, right there, based on that definition, what is my polarity across R3? What is the polarity on this side and on this side based on that definition? This side should be what?
Negative.
Negative, right color. So this side should be negative. What should this side be?
Positive.
Positive. And R1, what polarity should this side be?
Negative.
Negative. This side should be?
Positive.
Positive. Okay, now how about R2? What polarity is the top of R2?
Positive.
Positive, and the bottom should be?
Negative.
Because it flows from the negative to the positive, from the bottom to the top, the bottom has to be negative. Are we clear on that?
Yes.
Okay. Now let's go ahead and check our loops. Watch this. Okay. Loop number 1. And I'm going to add a few more points just so that we can be very specific. We already stated our points A and B, so I'm going to state, so this will be W, this will be X, this will be Y, and this will be Z. I'm just going to throw some other values on here. So my first loop, let's say I'm going to go from A to B to X to W back to A. So that's my first loop. The direction will be A, B, X, W, A. So I'm going in a clockwise direction this time. Doesn't matter which direction to go, but algebraically should work out. So if I start at A, and my next point is to go to B, what polarity do I encounter first?
Positive.
Positive. How much positive do I have?
1.75.
Okay, so let's 1.75 volts. Now I'm at point B. At point B, I have to go to X. So point B to X. Do I have any numbers to add there?
Nothing.
Nothing. How about from X going up to W? What's the first thing we encounter?
Negative 10 volts.
So I have to add a negative 10 volts to all of this. And now I'm at point W. From point W, I have to go back to A. So from point W, what's the polarity I encounter?
A positive
How much?
8.25
8.25.
volts.
But ladies and gentlemen, in that particular loop, algebraically, what does this add up to?
0.
0 volts. So far is Kirchhoff happy with us? Mr.
Yes.
Kirchhoff is happy with us. Now let's go ahead and check loop number 2. And loop number 2, I'm going to start at point A. I'm going to go to point Z, and go to point Y, go to point B, and going back up to A. So I've defined that. So A to X, X to Y, Y to B, B back to A. Is that one complete loop? Have I stated all the points of that loop? I have. Mathematically, let's see what we have. At point A going to point Z, what's the first polarity we encounter?
Positive.
Okay, we have a positive 9.75 volts. And we're going to add that to, what's the next? We're at point Z. Now we have to go from Z down to Y. What's the first polarity we encounter?
Negative.
Negative how much?
8 volts.
Okay, so we're going to add that to a negative 8.00 volts. Now we're at point Y going to point B. Is there any number to reconcile there?
No.
Nothing. And now from point B, I'm going back to A. What's the first polarity we encounter?
Negative.
What value?
1.75.
Negative 1.75 volts. Add that up, my friends. What do we have in loop B?
Zero.
0 volts. Is Kirchhoff happy with us so far? So far, he is. Can somebody call out the points for the third loop, the outside loop? Pauline, you want to call out those points for us? You can pick any point to start and just call them out. Oops, did we lose Pauline? Oh dear. Oh, we lost her. Oops, sorry. Andrew, what do you got?
Oh, we're frozen.
Oh, Okay, here, I'll call this out. I will start at point W, and I will go from W to A to Z,
We're frozen.
Z to Y, Y to B, B to X, back to W. So a whole bunch of points there, yes?
Yes.
So to follow this, W, A, Z, Y, B, X, W. So I'm going around the outside loop, yes? And if I go around the outside loop, let's see what we have. So W to A, what do I have? Positive
8.25.
volts. So from A to Z, what do I have? From A to Z, I have a positive 9.75 volts. Then from Z to Y, what do I have?
Negative 8 volts.
Negative 8.00 volts. From Y to B, B to X, there's nothing on this bottom wire. How about from X back to W? What am I adding? A negative 10.00 volts. Add all this up, what do I have?
0.
0.
Mr. Kirchhoff very happy with us.
Yes.
Kirchhoff's voltage law stated this. Kirchhoff's voltage law stated, in any closed loop, our algebraic sum of all voltages must add to 0 volts. And we showed that here when we first introduced Kirchhoff's voltage law, and we demonstrated that here with our circuit analysis for superposition. Kirchhoff's voltage law stands. One final thing and we're done, and that is Kirchhoff's current law. How about KCL, question mark, Kirchhoff's current law. And Kirchhoff's current law stated what? Kirchhoff's current law stated the sum of currents entering any node must what? Equal the sum of currents exiting that node. Well, let's see if that's true. From our summary document that we had done, from our summary document, did we have a summary of currents for all of these resistors? So why don't we put that information in here now? Do I have a current through R1? The current through R1 was 412.5 milliamps. 412.5 milliamps moving
To the left.
to the left. Do I have a current through R2? R2 was 87.5 milliamps moving,
Going up.
going up. Do I have a final current for R3? R3 was given as 325 milliamps flowing to the left. Does this reconcile? Do I have currents coming into node A? Let's go ahead and do our famous in-out chart for this information. What currents are going into node? This is for node A, for node A. What's going in?
3.25.
No, 325 milliamps.
I mean, yeah, 325 milliamps.
325 milliamps. Do I have anything else going into node A?
Yes, 87.5 milliamps.
87.5 milliamps. Do I have anything else going in?
No.
Do I have something coming out of node A?
Yes.
So that should be in this column. Works out to be 412.5 milliamps. So it looks like we have to do some addition here. So this will come down to be 412.5 milliamps. What do these two guys add up to be? $425 milliamps, 412.5 milliamps also. Is one side equal to the other? The answer is yes. Is Kirchhoff happy? Question is big yes. Kirchhoff's voltage law, Kirchhoff's current law are what's used to help substantiate your analysis of these final voltages, these final polarities, these final directions of currents, these final numbers of currents, all to be completely balanced when we're doing our loop analysis, and all to be completely balanced when we're doing our current analysis. That, my friends, is how we apply those principles to solve something like our superposition theorem exercise. So our superposition exercise is, in summary, again, used for circuits that have multiple voltage sources, but they're not easily reconciled as being series aiding or series opposing. They're not easily reconciled. You just can't say, well, how about we take the 10 minus the 8 and we'll have a net of 2. Well, you can't do that because they're not in series with each other. So how do you work something like this out? Through the solution method as stated, through those 4 steps. At the end of the 4 steps, at the end of step 1, you have this chart. At the end of step 2, you have this chart. And at step 3, you algebraically add. You take that information, you put it back onto a redraw of the schematic, pop the numbers in, do your loop analysis, do your current analysis, and guess what? What you learned about Kirchhoff's voltage law and Kirchhoff's current law helps you prove that the numbers you have here are in fact correct. Okay, that the numbers you have here are in fact correct. Any questions about this? You guys did great. I apologize for taking a little longer than necessary, but I appreciate you being patient with this process. You guys did great. So you will be seeing a separate analysis exercise that you will also be doing in multi-sim. So you will have more than just the wiring of the multi-sim exercise. You'll actually be building a multi-sim circuit and proving this in multi-sim. Okay? Any questions about that?